Hello students, welcome back. Lesson 3 is a continuation of Lesson 2. We're going to stay in Chapter 2 of our textbook, Probability. Now let's begin with a review. And if you're comfortable with Module 2 materials, then you can skip this video and go directly to Section 2 of this notebook. Otherwise, let's begin a review from the axioms of probability. Here we go. Let's begin with a non-empty set S, which we call the sample space. Furthermore, we're going to call the elements and the subsets of S the outcomes and the events, respectively. Now, the probability is a set function defined for all subsets of S with these conditions. Number 1, the probability value is always between 0 and 1 inclusive for any event. Number 2, the probability for empty set is 0 and the probability for entire sample space is 1. Finally, the addition rule. If you have a disjoint sequence or mutually exclusive sequence, A1, A2, A3, A4, and so on of all those events, then the probability of that disjoint union is the same as the sum of the individual probabilities. Now the key word here is disjoint union. No matter what pair we select, we have to have empty intersection. Otherwise, this is no longer true because there will be some overlap that may be counted twice, 3 times, and so on. This one is called the addition rule. And as for this one, please remember, this part was not totally necessary. So our textbook author skipped this part and proved it instead. This one is necessary. And as for the first rule, this part was necessary, so our textbook author assumed all those. This part was not really necessary, we could actually prove it. Now, how about some examples? For finite sample space, the relative frequency is a perfect example. The number of outcomes of an event over the total number of outcomes of entire sample space. Like this example, roll a couple of dice and then, count. Alright, now what if you have infinite sample space? In that case, straight up counting is meaningless. So we have to rely upon appropriate measurement depending upon the circumstance. And in this particular example, dartboard example, I hope everybody remembers, this is 2D, so the measurement here is area. Now, if you have something in 1 dimension, you'll have to use the length. And when you use something in 3D, so it's going to be volume and so on. So the area of the square over the area of the entire circle. Alright, so much for elementary examples and the axioms of probability. Now that's enough for most people, but there may be some students who want to dig just a little bit deeper, particularly considering the explanation I gave you is partly wrong. And here's an attempt to make everything right. And the previous description is okay for finite sample space or discrete sample space. For uncountable sample space, on the other hand, things can go bad. And even for this kind of elementary example, the dartboard example, things can go bad. So, how do we make it right? It turns out the problem is we cannot, in general, make this probability set function well defined for entire power set. So you cannot consider the probability for any subset of S in general. In some extreme cases, there are some subsets of the sample space S that is not an event and cannot be considered appropriately with the probability set function. You have to screen those out. Consequently, you have to restrict your domain and bring in a new subclass. Now, if you bring in something new, then you have to have additional conditions for that domain. And that's what this new set of axioms is all about. That domain, that new domain, must satisfy these three axioms, A1, A2, A3, and then the set function P must satisfy these three axioms, which we discussed before. So total, there are 6 conditions to check, not just 3. So this is a proper definition of the probability, and if you express it in terms of axioms, then not just 3 axioms, but there are 6 axioms to check actually. Alright, so much for the remedy, and let's go to the next topic. Odds. Okay, review on your own, it's not that important. Next, rules of probability. Now there are 3 rules of probability, or 3 categories of rules of probability rather. Addition rules, inequality rules, and then the multiplication rules, which we're going to discuss a bit later. Now how about the addition rule? Well, they're all coming from the third axiom here, which is basically an addition rule for infinitely many events, A1, A2, A3, A4, and so on, if they're all mutually disjoint. If you have just 2, then you can simply add up the probabilities. Here's a visualization. Now what if there are some overlaps like this? In that case, you can decompose so that there's no overlap and then add them up like this. Blue crescent, red crescent, and purple football separately and adding them up, again using axiom 3. Or you can just add up the circles, entire blue circle, entire red circle, and subtract away the middle part, which was counted twice. Either way, it works out. Finally, the complement events. Not A can be obtained by 1 minus the probability. And this comes from not just axiom 3, this one, but also from axiom 2, especially this one. The probability of the entire sample space is 1, and that's necessary because this one is coming from the probability of the entire sample space. Okay, so much for the addition rules, and let's go to inequality rules. When an event is more inclusive than the other, then you have an inequality. Here's a visualization. Next, what if you have a union that is not a disjoint union in general? If you have disjoint union, then you have this axiom 3. The probability of the union is the same as the sum of the individual probabilities. But if you have overlaps, then this part, sum of the individual probabilities in general, greater. Why? Because there are some overlaps that are counted twice, thrice, and so on. So if they're all empty, then you have equality. And of course, in that case, these unions are all disjoint unions. Okay, so much for inequality rules. Now what do we review? Conditional probability. Okay, here we go. Here's a definition of the conditional probability, but it's a little bit difficult to see the way it is. So let's go through an example problem, which we already did, but let's go over it as quickly as possible. Let's consider this example again. Hypothetical group of 30 college students, and if I select one student at random, then it is out of total 30, the entire sample space. So among those 30, how many female liberal arts students? There's 6. So that's my probability, 6 out of 30. This is just a straight up probability, not conditional probability. Now what if we impose a condition that restricts the sample space? Like this. If the selected student is female, so women only, you have to cross out all men and the total, and then just consider women only out of all those. So how many women are there total? No men, just women. There are 12. And among those 12, 6 liberal arts students. So we have this new probability compared with the previous. We have new denominator. Basically, we have restricted sample space, smaller sample space. Now, what if you have another condition like this? Liberal arts students only. Just ignore business and technology students, just liberal arts only, first column only. Then total is 11. So what do we have? We have 6 out of 11. And this denominator comes from the condition. So we get new sample space. Previously, we had different conditions. So 12 is a new sample space. That corresponds to female students only. And under the new condition here, this time, new sample space is liberal arts students only. So that's the new denominator there. And that's what this conditional probability is all about. Restricting the sample space into something smaller. So basically we are changing the denominator into something different, something smaller. Now, what if I flip this denominator to the other side? Then you can get a multiplication like this. So from here, flip it over, we get that. Then this is called the multiplication rule. So probability of A and B is multiplication of these two. If you switch characters, then you're going to get the second expression, the same thing. Now, one final comment. A special case when this A given B, probability of A given B, this conditional probability happens to be the same as straight up probability. So this blue is same as this blue, and then, excuse me, I did it wrong, this one. And then this should be red. Okay, probability of B, that doesn't change. Compare these two, conditional probability of A given B, the blue one. If this blue one is the same as this blue, the probability of A given B is the same as just straight up probability of A. Then we get a little bit simpler expression because the blue part, this part and that part are the same. So the probability of the intersection A and B is the probability of A times probability of B, just straight up multiplication. That's another version of multiplication rule that applies for when event A and B are independent. In general, we have to multiply the conditional probability. For independent case, we can multiply, straight up probabilities. And that's because, of course, this blue and that blue are the same. Examples of this independence, that was earn model with replacement. I hope everybody remembers. Of course, we're going to discuss that in a little bit more detail here in section 3. So I'm not going to talk about it at this moment as a review. Alright, so much for the review. And let's meet again soon in section 2 of this notebook. Stay tuned.